now that the fundamental theorem of calculus has shown us just how important antiderivatives are, we're going to turn our attention to a technique that allows us to find the antiderivatives of more functions than just the ones that are in, standard tables, right? Where we essentially are just reversing our basic derivative rules, right? In some sense, I guess you could even put this technique in that same category of reversing our derivative rules, but it also comes with a step-by-step process, right? Because sometimes it might not be as easy to look at a particular function and figure out how to work backwards and find its antiderivative, right? And the substitution technique, what it does, it gives you a way of reversing the chain rule. So let's remind ourselves of what the chain rule is. So recall, and again, I'm not going to state the specific requirements of the function, but let's say we had a function that's a composite, right? Where you have one function f being evaluated at another function g of x, right? So again, this is just the fancy word for this is that it is a composite. Well, we have a rule that tells us how to differentiate composites like this. So if this is our function, then its derivative can be written as dy dx is equal to f prime of g times g prime, right? So in words, when you're evaluating the derivative of a composite, what it says is take the derivative of the quote-unquote outer function, evaluate it at the quote-unquote inner function, and then multiply that by the derivative of your quote-unquote inner function. I think I just met my quote-unquote quota for the day, and I promise no more bad jokes. All right, so that's the chain rule, and in many times when the chain rule is being introduced, we define this inner function, we call it u, right? So we call it u. Okay, so that's a y, not a u. So we call that u, right? So essentially we just kind of name it like this, and what that means is we can rewrite our original function in terms of u. So y is f of u, and then there's another way this derivative can be written. So for instance, if I want to find dy dx, I can take the product of dy du, so differentiate y with respect to u, and then multiply it by the derivative of u with respect to x, right? And even though our derivatives here, they're not true fractions, they're differentials, just from a very heuristic standpoint, you could say, well, the du's cancel out and you're left with dy dx on that side. Not very precise, and yes, for an introduction to that idea, that's a little rule that you can think of. But as you go deeper and you study something called differential forms, then you realize, well, I can't really do that, right? Or can't think of it that way. Okay, so that's our chain rule. So the whole idea now is what if we had a function that kind of looks like this, and we had to integrate it? If it's not too complicated, maybe we could just look and tell what the antiderivative is. But now what we're going to do is describe a technique that you can follow certain steps, right? Provided you're starting with a function like this and you're trying to work backwards to the original one. All right. So just to give you a sense of why we might utilize a technique like this, I want us to consider two antiderivatives, right? So let's say I have 2 times the quantity 2x plus 10 squared dx. So I have to do this, right? Well, what I can do, this power isn't very large, it's only 2. So what I can do, I can actually expand this binomial. So I can use algebra and expand this and make it so that it's really just an easy term by term antiderivative. When I expand 2x plus 10 squared, I will get 4x squared plus 40x plus 100, and then I have to have my dx, and now distribute the 2. Now I have a choice. I could factor out the 2, but again, I just want to show you that with a few simple algebraic steps, I can rewrite this integrand to something that is very straightforward to integrate. So 8x squared plus 40x plus 100. Well, actually, I didn't distribute my 2 here or here, so it will be 80x and then 200, and then I have my dx. So then I can integrate using my power rule term by term. So this is 8 over 3 x cubed plus 40x squared plus 200x plus c, right? So not too bad at all. But now, what if I change just one thing in this problem? In fact, if I change this exponent, and instead of having it be a 2, why is that? Was my thing doing that? Right. So consider this one as well. What if I keep the 2 there, keep the 2x plus 10, but I make the power 200, for instance? What are we going to do? Well, we could start expanding, and what that means is we would have to write down 200 factors of 2x plus 10 and foil and foil and foil, and then maybe after a while your kids could pick up the foiling and they could foil and foil and foil, and then eventually your grandkids could foil and foil. No, it wouldn't go on for generations, but it would certainly be faster than the almost less than a minute than we did this particular problem in, right? So the thing is, even though algebra, we kind of know what we could do, just using algebra isn't very effective at all, right? But I want you to take a look at this expression here. So let's really parse out this integrand, and I'm going to do it on this side. Notice there is a composite in here. I have the 2x plus 10, and that's all to the 200th power. Again, that's the idea of applying one function to another function. Here, the two functions are these. You have your linear function 2x plus 10, and then you have your power function, something to the 200th power, right? And we've combined these two to make a single function. Not only that, but we have this extra constant here. That extra constant, this times 2, is actually related to the inner part by the derivative. So really, if I take a look at this, and if I think of this as my g of x, or if you want to use u, right, whichever symbol you want to use, that looks like my inner function. And then out here, I am multiplying what is actually I'm multiplying by what's actually the derivative of this inner function. So right here is my du dx, or if you want to write it as g prime of x, right? So it looks like it fits that pattern for my chain rule. In other words, this looks like the answer, right, that I would get by applying the chain rule to some original function. And the thing is, can we figure out that original function not by using tedious steps in algebra, by being efficient and using or looking at our chain rule pattern and using it in reverse, right? So this is what we're going to do, right? So I'm going to call this, just like I would back in Calc 1, I'm going to let u be equal to the inner part, 2x plus 10, right? And then if I differentiate this, right, so I'm going to write down my du. I know what I'm going to get, so du dx is just 2. But then what I'm going to do is write this. I remember one of those concepts from your first semester of calculus was the idea of differentials, where you can essentially write this derivative in differential form. So this tells me that du is equal to 2dx, right? That little trick where you kind of treat it like a fraction and multiply both sides by the dx. Again, not really a fraction, right? However, in many respects, we can treat it like a fraction. Okay, so how does this little trick help, right? How is this anyway related to the chain rule? Let me take the integral here and rewrite it just by doing one thing. Since this is a product, we have the commutative property of multiplication, where I can change the order, right? And don't forget, there's a product here too. So I can change the order here, I can group them in a particular way, and this is how I'm going to do it. I'm going to put the quantity 2x plus 10 to the 200th power. I'm going to put that factor first. I'm going to put the 2 in the middle, and then I'm going to have the dx right here. All right? So now, if we are, this is where we get to be clever, right? But we don't have to be too clever, we just have to be very observant. If I take a look at the inner part, right here, it's this. This is right here, right? In fact, that's why I chose that 2x plus 10 as my u. Next up, look at this. This product is right here. So, if why is this process called the substitution technique? Because now what I'm going to do, I'm going to do a double sub, right? A double sub, that sounds fun. I'm going to take the expression 2x plus 10, and wherever I see that, I'm going to replace it with u. So I'm going to plug a u in right there, right? And then wherever there is a 2 dx, I'm going to just replace it, right, with du. So in other words, I'm going to replace this differential with a relatively simpler differential, just du. And I'm going to replace the inner function 2x plus 10 with this new variable u, right? So let's write that down and see what happens. So here is where my substitution takes place, and it's two things that I'm substituting. One, I'm transforming this part of the integrand into, and then it just becomes u raised to the 200th power. And then here I'm transforming this differential into a different differential, but in terms of u. So this would be times du. And now I look at this and say, yeah, in some ways I have simplified the integral, but not by factoring out and expanding an immense product. No, it's by cleverly switching from an antiderivative with respect to x to an antiderivative with respect to u, right? And for some, and that's why for some authors and people, they refer to this as a change of variable. So you're changing everything that was originally in terms of x, we're now changing it to something that's going to be in terms of u. So it's sometimes referred to as a change of variable. And now this is something that we can use our standard, our basic power rule, right? And in this case, using our power rule, so add 1 to the power, it now becomes 201, and then divide by 201. I always like to put my coefficient in front of the variable, right? But you could certainly put it as a single fraction, and then don't forget our plus c, right? All right, so we've now done the calculus part, right? But we're not quite done yet, because remember our original problem. Let me restate the original problem. It's the antiderivative of 2 times the quantity 2x plus 10 to the power 200 with respect to x. So I would like my final answer to be, again, the original function, which would have to be in terms of x. So how do I do that? Well, just reverse the substitution. Reverse the substitution and say, now that I've taken care of the calculus part, use the same u that I have up here, but now switch all the u's back to 2x plus 10. So then we write our final answer. So now this is equal to 1 over 201 times the quantity 2x plus 10 all to the 201st power and then plus c, right? And if you were to take the derivative of this, and I do encourage you to do it, pause the video, check, do the chain rule on this, and show that you get back the function that we started with. So essentially close that loop. We now showed how you can, again, with this clever observation of inner functions and differentials, when you put these two ideas together, we can take what seems like a daunting and difficult type of problem and reduce it to something that we have a specific formula for. And then once we've solved it, switch back, right? It's like the sleight of hand. It's like you're a mathematician, right? It's like, ooh, where did the u come from? Oh, where did the u go? So you kind of use the u as this temporary change of variable to make the integral easy to work with, but then you state your final answer in terms of x, right? So let's do this. Let's now, like I said, there are some key steps in this process. Let's outline the steps. So let's call, we can call this a procedure or, a set of guidelines. Now these are not hard and fast. Sometimes you might have to do a little modification. Problems always get a little tricky, right? But then that's what examples are for. So you do a couple of the standard ones to get used to the procedure, and then you test yourself by doing the trickier ones to where you get really, really skilled at the procedure, right? So just think about like riding a bike. First you got to learn how to balance and pedal. A couple of years down the line you're popping wheelies, you're riding with, not holding the handlebars and all that stuff. That what we're about to do is the mathematical version of that. So the first step is to, if we're given, and I'll start with I'll say the indefinite integral or antiderivative. There is a version of this when you have a definite integral, and we will look at it. But let's say we start with an indefinite integral. And let's say that it's involving a function, like say f of g of x. Right. So that's the composite. What we're going to do is identify, again, that inner function, the g of x, and you can call it either g or you can call it either u. So identify u equals g of x, right? And that's the first thing we did up there. We identified our u as the 2x plus 10, that inner part, right? And then we are going to find, right, the differential du, which I can write it down symbolically. The differential of this is going to be g prime of x times dx, right? So find this differential and substitute the u that we picked in step 1 and the differential that we computed in step 2. So, and substitute, or change the variable, and substitute u and du into the integrand, right? Well, actually, it would be, let's say the integral, right? Because we're switching both the function and the differential, right? And then what we're going to do in the third step is to integrate this, what is hopefully an easier integral. So evaluate the integral with respect to u. So evaluate the integral WRT, so with respect to u, and that's good. Again, don't forget your plus c, but that's not the last step. What we have to do is do that reversal. So we're going to say, you can either say reverse the substitution or write the final answer. So let's say write the result. That's a little bit more compact than saying the final answer. So write the result in terms of x, right? And how do we do that? We use the same expression that we started with up here, the same u, right? And this is your procedure for the substitution technique, right? And the only thing where it can get a little tricky, and we'll definitely look at examples of it, would be is in that kind of second step, because sometimes it's not entirely clear how I do this substitution, right? But if you keep this in mind, then we'll be able to do it. All right. So let's go through and do some examples. Right. We'll get a few examples in. So let's look at, let's say, example 1. So let's say we have the integral of 2x plus 3 over, and since we love square roots, let's put a square root in there. So we got x squared plus 3x plus 5 dx, right? So the first thing that helps, particularly when you think about the way that we typically write our formula for the chain rule, it's written as a product. It's something times something else. But right now this is written as a quotient. So this is what I'm going to do. I'm going to keep that quantity there, and then I'm going to rewrite this and get that radical out of the denominator and write it as a product. So this is how I'm going to do it. If I write all of this to the 1/2 power, right, the x squared plus 3x plus 5 to the 1/2, and then apply my property of exponents and flip it, I have to change that positive 1/2 to a negative 1/2. So then it looks like this: x squared plus 3x plus 5 all to the negative 1/2 power, and then times that quantity that I had there, the 2x plus 3 dx, right? And again, it's important to use, when you rewrite it this way, it's important to use the parentheses, because that tells me that it's this entire quantity times this entire quantity, and then times the dx. So now what I have to look for is the pattern of an inner function, right? And we want to see if the derivative of what what would likely be our inner function is that derivative outside here, right? So in other words, we're looking for a g, right, which looks like this, and then a g prime. Because do you notice that if I take the derivative of what's in the first pair of parentheses, I get exactly what's in the second pair of parentheses. So I can see it's set up perfectly for this method. So let's execute the method. So let u equals x squared plus 3x plus 5, right? Then the next step is a given. Got to take our derivative. Why do we need a derivative? Because we need to figure out what du is. We can't just change this part of it because we can't have a single integral in terms of two variables. So I can't have a u here and leave all these x's here, right? And I can't just throw away the dx. I mean, that's just, flat out rude. But so our du in this case is 2x plus 3, and then time that quantity times dx, right? So I just do my differential form in one step, right? Bring over the dx. So then here is the substitution. So all of this right here is now going to be my simple du. So I'll get rid of that 2x plus 3 times dx. Everything there just becomes du. And then the u goes inside the first pair of parentheses. So the x squared plus the 3x plus 5, all of that just becomes u. So much like our first example, we're going to end up with a very simple antiderivative that requires just the use of the power rule, right? So let's write it down, right? So this is going to be, so we're pretty much at step 3 now, right? We're going to evaluate the integral with respect to u. So I have u to the negative 1/2 times du, and I'm integrating that, right? And we've got it to a point now where all we need is our power rule, and we will be able to do our antiderivative. So adding 1 to this, right? So it would look like this. Negative 1/2 plus 1 is a positive 1/2. Sometimes you might want to write it like that, and that's fine. But I always encourage you to especially if you end up having to do more with the antiderivative, you want to keep it as simple as possible. So instead of writing it like this, I can write it as 2 times u to the 1/2 plus c. And as far as our completion bar in this problem, we're like at a 99% completion, right? So let's make it 100. And the way we do that now is by reversing our substitution. So wherever there's a u in this, and I can't say the final answer because we're not right there, but here's a u, what I'm going to do is plug this in right there. And then I will get my final answer in terms of x. Right? So then this becomes 2 times, and I'll write it as the quantity x squared plus 3x plus 5 all to the 1/2 power, and then plus c. And if we wanted to write our final answer like the original with the radical, we could do that, right? Just go back and note that the 1/2 power is equivalent to the square root function. So then it's a square root of x squared plus 3x plus 5, and then we have our constant of integration, right? So that, again, a straightforward application of it where we didn't have to do anything to modify it. Now let's do one last example where it will require a slight modification. So here is x times the cosine of x squared dx, right? So here we have x squared times the cosine of x squared, and there's a product there, right? And don't be tempted to try to integrate the x by itself and then the cosine of x squared by itself. In fact, the reason, if there wasn't an x there, in fact, you couldn't integrate this by itself, right? So you can't, there is no product rule for antiderivatives. What we have to look for is a certain pattern, and in this case we see that the pattern is close to what we want, right? I'm going to define my inner function to be x squared, right? So I'm going to do this. Well, in fact, before I do that, let me even write down a slightly different version of this. Again, using that commutative property of multiplication, I want you to think of it like this. All right? Because what we're going to end up, I'm going to tell you what we're going to do, right? I'll let no secrets amongst friends. We're going to end up replacing this. Instead of having a constant times a differential, we're going to end up getting, instead of a variable times a differential, we're going to end up having a constant times a differential, and that's going to be easier to work with. And we're going to replace this, x squared, right? So let's go ahead and do that. So let's make our u, in fact, yeah, we could do it under this one. So let u be the inner function x squared. Here's my differential of u. It's 2x, and I bring over the dx, and there we go. Now, unlike the first example where this differential was exactly what we needed in the problem, this one has an extra 2. It has this extra constant that's not anywhere in this integral. So there are several ways you can do it. The way I like to do it is that I modify this equation to fit the problem. There are ways that you can fit or modify the problem to fit the differential. It works out to be algebraically the same. So I look at it this way. I want to know what x times dx is. Now, since there's a 2 here that's multiplying the x times dx, if I divide both sides by 2, or if I multiply both sides by a half, what I will get on the left-hand side is 1/2 du, and then what I'll have on the right-hand side is x times dx. And that's exactly what I have here. So this is what I was saying earlier. This variable times dx can now be rewritten as a constant. In this case, the constant is 1/2 times du, right? So that's one substitution. The other substitution is more obvious in that the x squared here, just turn it into u, right? And then so let's see what the integral looks like when I now convert everything over to be in terms of u, right? And again, I want to emphasize that we can't just change that part and ignore the other parts that are in terms of x. Everything has to be converted over, right? So let's write that down. We have cosine, now we're going to write of u, and then instead of writing the x dx, I'm going to write 1/2 times du. And the reason why this 1/2 is easier to work with is the fact that we have that property of antiderivatives that allow us to pull the 1/2 outside completely, right? The thing is, we couldn't have done that with the x up here because, again, we were integrating with respect to x. So this is not a constant, but the 1/2 is a constant. So I can write it like this. So it's 1/2 the antiderivative of cosine of u du. And now I can find the antiderivative of cosine of u with respect to u. That's one of our basic trig antiderivatives. So what do I have? This is 1/2. The antiderivative of cosine is a positive sine of u, and then we add our plus c, right? And then it's not complete until we write our final answer in terms of x. So what we're going to do, wherever there's a u, we're going to take this and just plug it in right here. So then our final answer in terms of x is 1/2 cosine of x squared plus c. And again, if you were to use your chain rule, take the derivative of this, you'll see that we will get, oh, why did I did something. I'm glad I caught that right at the end. This doesn't change. Oh, no, eraser. This is the sine function. Yep. So it's the final answer. The correct final answer is 1/2 sine of x squared plus c. And if you took the derivative of this, use your chain rule, you're going to get back the original, which was that x times the cosine of x squared. Right? And that's the substitution technique for antiderivatives. In the next video, we will take a look at what can we do when we now have a definite integral. There are two approaches. There's one that I prefer because that method works beyond even just Cal 2. Like if you have to go on to multivariable calculus, the concept behind the second approach is a lot more general, and I would recommend using that. So if you want to see what that method is, tune into the next video.